Hello everyone. My name is Simon Stadler. Welcome to today's meeting of Pi and AI. Before we start, there's a short intro video I would like to show you. So let's get started right away. And it seems I've closed the videos. So let me open it up for you again. Here we go.
Hello, deep learners. I'm Andrew Ng, founder of deeplearning.ai, and I'm excited to welcome you to our global deep learning community. I know that many of you are here today because you want to break into AI and build your career. I hope that being part of this community will help you to do so. To give you a proper welcome, I'd like to show you around the deeplearning.ai offices and meet some of the teams so that you can see where it all happens.
Oh, hi, Andrew.
Do you want to tell our friends at Pine AI what you do at deeplearning.ai?
Sure. Hi, everyone. I make articles and other media that help people learn about AI and help them understand the huge impact that AI is having in the world. Today, I'm putting together the next issue of The Batch, our weekly newsletter, and I'm looking for the biggest stories of the week to keep our readers informed.
What's been the most surprising thing you've run into working on The Batch?
How much is going on in this field? There's never a dull moment. You might think from the outside that machine learning engineers really understand everything about AI, but nobody understands everything about AI because this field is just coming to life right before my eyes as I put this thing together every week.
All right, I know you're really busy, so let's you get back to it.
Thanks. See you later.
Let's go meet Kian, who helped me create the deep learning specialization. He's working on an exciting new project. Hey Kian, so do you want to tell the people at Pine AI what you're working on?
Yes, sure. I'm leading a project called Workera, focusing on helping people get offers in AI and navigating their career by testing their skills, preparing for interviews and certifying them, as well as matching and referring them to good jobs in AI.
That's really cool. And what's the most exciting part of your day?
You know, the AI field is new, organizations and jobs are still misunderstood, so I'm excited to help people understand what different types of jobs exist in the field, what tasks they will work on, and what skills are needed to achieve those tasks.
And that's really important work. Well, it's nice chatting, and now let's go chat to Hotel, who is on their product team.
Hey, Andrew.
Do you want to say hi to our friends at Pine AI and let them know what you're working on?
I would love to. Hi, everyone. I lead the product team in deeplearning.ai, where we create AI education content accessible to people all around the world. People like you.
And what are you most excited about right now?
I am so excited to see our community grow and to see how eager people are to learn more about AI.
Thanks, also.
Thanks, Andrew.
So, as you can see, our team is working hard to support you and help you learn. It's never been easier than before to break into AI. So if you want to build a career, you can leverage online resources available, including open source code, datasets, papers, and online courses like a deep learning specialization on Coursera. As part of this journey, I hope you get your hands dirty too. Don't be afraid of diving in to build your own project, or go ahead and try to replicate a research paper that you're excited about. One thing that I've seen help a lot of people succeed is if you can build a community or find a community of fellow deep learners you can meet with and study with on a regular basis. In fact, I hope that this Pine AI meetup that you're at right now will be a good place for you to meet these people. I hope you enjoyed the event today and that you learn a lot, both from the talks and from each other. And once again, welcome to the deeplearning.ai community.
Do you have audio now? And I should also, okay, now you have audio and video, hopefully. Please tell me in the comments. Okay, perfect, thank you. Again, today's talk is going to be about beyond stochastic gradient descent. We're going to look at higher order optimization methods for machine learning processes. So about me, I'm a master's student at the TU Graz in the field of technical mathematics. So what you're going to see today is going to be a bit more in the direction of mathematics rather than informatics. But don't worry, I'm going to try to keep it on a level which is understandable for everyone. I'm currently writing my master's thesis on exactly what you're going to hear today, namely on quasi-Newton methods for machine learning. And I'm supervised by Professor Florian Mandl at the KFU. Apart from my studies, I also work at the AVL, where I'm happy to be part of the team of Herbert Danzinger, who is also joining us today during this talk. All right, so let's dive right into it. What am I going to talk about today? The contents of my presentation today is going to be a short overview about the structure of neural networks. I'm pretty sure most of you are already familiar with this, but I'd like to recap it anyway, because since we're diving into the mathematics of this, it's good to have everything refreshed once again. Then I'm going to give you a really short reminder on what is gradient descent, and then we'll go into the topic of higher order optimization, and we'll also have a look at some code which is actually available on GitHub, so I will post a link in the chat afterwards once we get there. And in the end, I will also show you some numerical results. That's the part where we get some pretty pictures. So we can basically look at how the different methods compete with each other and what the run times and convergence speeds are. All right, let's go to the first topic, the structure of neural networks. So far, I've only delved into the topic of quasi-Newton methods for deep neural networks. Anything else is still to do on my list. So I definitely do want to do this in the future. But since dense neural networks provide a really nice and simple structure, all right, yeah, perfect. Thanks, Herbert. So since dense neural networks provide a simple structure and it's easy to write code for them, I started with these. All right, it seems the stream is a bit behind for my with my slides. Do you see the mathematical formulation right now, or is it the picture? Math, perfect. So just correct me if I'm wrong. You see the number of layers and the number of neurons in layer L. Is this correct? Okay. I seem to be having some discrepancies between my two monitors. So, all right, now it works. I just have to wiggle my mouse a bit, then it switches. All right. So for the mathematical formulations, we have some very basic definitions. So we define the number of layers to be L. We have a given number of neurons in each layer L. So if you go back to this image of a dense neural network, we have some input layer, we have a number of hidden layers, and an output layer. And the number of these hidden layers and the output layer is going to be called L. The input layer is just a separate layer. We don't really consider this at all. And the number of neurons in each of these layers is going to be denoted by NL. So we have NL, number of neurons in each layer L. And since we're looking at a dense and linear layer, linear network, we have some matrices for weights, which give us the connections between all the layers, and some biases for each layer. Now, so what does this look like in a more in-depth sense? So we have some activations which we get out, and our input is going to be the 0th activation, and the output is going to be the 11th activation. And then we basically do a forward pass through our network, so we compute all the outputs iteratively. Always the 11th activation is some nonlinearity for the layer L applied to the matrix L times the previous activation, so AL minus 1, plus this layer's bias. And this is the structure we're going to work with from now on. So just for clarification of this whole thing, the output for the first layer for some input x is going to be sigma 1 of wx plus b1. And what we're actually interested in is the prediction, so the output of the whole network for some input x. And we denote this by y tilde, but we don't really use y tilde. We are going to use f of x, since we're looking at this as a function in x. And this is the entire mathematical notation of what our network is going to do with this input x. So first, the weights are applied. It says the broadcast is ended. Okay. Yeah, on my side it should be working as well. I think I'm just gonna keep talking. Okay, perfect. So as you can see, this output is this huge chain of linear functions. So this b1 plus w1x is a linear function and some non-linear activations. And we're going to work a lot with this f. So one side note on this as well. So yes, the video is going to be shared afterwards. So one note on this f, even though it doesn't say so here in this part, we always have this implicit dependence of f on the parameters of the model, so on these WL and BL. And that's going to be important, especially on the next slide, where we now look at the cost function. So for training a neural network, we always have some training set, which consists of training inputs and training outputs. And for everything we're doing today, we're just looking at the simplest cost function imaginable, which is, or actually not the simplest, but one of the cost functions with the nicest properties, the quadratic, or as it's also known, the mean squares cost function. So this cost function here, we bring in the dependency on these weights and the biases, is defined as a weighted sum over partial costs. And these partial costs are nothing else than the squared norms of the output, the expected output, and the prediction of our network for the given input. Now remember, on the previous slide we said that the weights and biases implicitly go into this f. So the cost function is actually not really so much dependent on output and input, but mostly on the weights and biases. That's what we're interested in. All right. And since we're going to talk about optimization today, here is the problem, our optimization problem we are going to talk about. So we want to minimize our cost function. So in the end, we want to minimize this sum of quadratic terms with respect to the parameters. And note here, as I said already, the xi and yi are given and they are fixed. We do not modify them for our optimization. All right, so let's get into the first part, gradient descent. This is the part you probably all know about, but I'm going to give a short intro anyway, because a lot of these parts are going to play into a higher order optimization as well. So for this, we assemble the weights and biases into one huge vector R. And then we do some Taylor expansion or linearization of the cost for a small step size delta R, or actually a small step, we should say, because the step size is something, is a scalar, and the step is a vector. So then we can approximate our cost from our current weights plus some weight update by our current cost plus the gradient of the cost at our current parameter with our current parameters transposed times our step our step delta R. And for classic gradient descent, we choose delta R to be in the direction of negative gradient. So this delta R is going to be minus some learning rate eta times the gradient of C at R, so our current parameters. And then our new cost is going to be approximately CR minus eta times gradient CR transposed gradient CR. And note this term back here is always going to be negative for positive learning rates. And so this term on the right-hand side is going to be strictly smaller than CR. And if we make this step size small enough, then this approximation gets close enough and we end up with a true descent method. So that's the idea of gradient descent. And of course, there's stochastic gradient descent, where you do not take into account the full set of training samples, but only a part of it. But this is something that need not be talked about in this setting all too much. All right, so some points about gradient descent. Gradients can really easily be computed via backpropagation. Probably all of you have heard about the backpropagation algorithm. This is rather simple. Plus, there is a really simple structure for the update. You only have minus learning rate times the gradient. So it's really easy to implement as well. And since you only have to store the single gradient vector, it is also rather memory efficient. And these are all things that are not really given for higher order methods, as we are going to see later on. All right, let's dive right into higher order optimization methods. So the classical higher order optimization method most people hear about sometime is the Newton's method. I've given you here a short pseudocode for the Newton's method. So we have some given function f, which in the setting of machine learning is going to be our cost function, which we want to minimize. And we have some starting vector x0, which in our context of machine learning is going to be the parameters of our model. And then we do some iterations. For every k, we first check if the gradient of our function at our current point is 0. If this is the case, then we are most likely already at a minimum. Of course, there's things you have to take into account as well, but this is the classical pseudocode for this. So if we're at the stationary point, then we set our solution to this xk and we break off the loop. Otherwise, we solve the following system of equations. The second order derivative of f at our current iterate xk multiplied with dk, this should be minus the gradient f at our current iterate xk. And we solve the system for dk, so for our direction vector, so to say. And then we update our vector, so in our case, our model weights with the previous model weights plus this search direction. And we do this until either this is satisfied or in a more practical setting. So for actually programming this, you would check for is this gradient small enough. Now, of course, you might see already several problems. This second derivative here is really hard to compute for certain models, or actually, in the case of machine learning, probably for all models. And it might not be guaranteed that this is always a descent direction. So here are again the major drawbacks. So computing the second order derivatives is always really hard. And one also major drawback is this procedure only converges locally. So there are things you can do to make it converge globally, but for this algorithm to converge, we already need to have our starting vector somewhere in the vicinity of our solution, of our minimum. Now there are some fixes here. So for the first one, we fix this by actually not computing the second derivative, but we only approximate it using the first order derivatives and zeroth order derivatives. And for the problem of only local convergence, we introduce so-called line search methods to select step lengths which guarantee that we always have some descent method, so that we always have a descent direction. If we put this together, we get a new pseudocode, and don't worry if all of this seems kind of vague. It is intentional because the theory behind this is all very complex. You could talk about this for hours and hours on end, without end. So here's the pseudocode for a so-called quasi-Newton method. Here it's basically more or less the same with two differences. So we again have this loop, but here we do not solve a system with the second order derivative, but we select some arbitrary invertible matrix H and then solve this system. Now this arbitrary matrix H, of course, has to be selected in a certain way that the method actually converges. And there is a ton of methods available. I'm going to mention a few of them in my talk on the slides to come. And in addition to not having the second order derivatives, we also select some positive step length, which we then multiply in front of our selected step. And the rest is basically the same. So let's get into some matrix update strategies. So I've said this matrix HK is basically arbitrary, but in order to get real convergence, you have to follow some certain rules. And there are some update strategies, for example, the rank 1 update and the inverse Broyden, Fletcher, Goldfarb, and Shano update, which are of the following form. So our initial matrix H0 is chosen at the beginning, and it's often just chosen to be the identity matrix. And then in each iteration step, we perform some update. So our next matrix is going to be some function of the previous matrix, our search direction, and the gradients at our current iterate and at our next iterate. So maybe let's go back for a moment. The update is going to end up here. So what we're actually looking at here is the gradient of our current iterate and our previous iterate. So this is going to come out in the code later on. Don't let yourself be confused too much. And often these are relatively simple updates, so this function is often chosen to be something linear. For example, the rank 1 update is simply going to be this matrix HK plus some linear combination of these vectors. All right, that's everything I want to say about matrix update strategies, because you can get really lost in this topic. If you want, you can Google about these rank 1 updates and the Broyden, Fletcher, Goldfarb, Shano updates. There is a whole lot of theory about those. And it's actually quite interesting if you're interested in the math behind it. And there's also some line search strategies. Line search meaning that basically you have your search direction in which you want to move. And along this line, you now want to find a certain step length. So you make this step length small enough, go into this direction to actually have a descent direction. So the cost function actually gets smaller. And I just mentioned here some popular line search strategies: the Armio method, the Powell-Wolf method, Barzilai-Borwein method. These are all used in combination with different matrix update strategies. And they only work sometimes in combination with certain update strategies. And also, again, there's a lot of mathematical theory behind this, which I do not want to go in depth during this talk here. Let's maybe look at some code right now. So basically, the idea is the following. So this is first now just an overview of what the code looks like. So we have some input, we have a model which yields an output. From this output, we can compute a loss or a cost, so to say, and this is what we actually want to minimize. So we have, so this model is what we want to optimize, and the cost is what's actually telling us how good the model is. And completely outside of this whole thing is our optimizer. So for the code we look at right now or afterwards, for the quick demo, we have some linear layers, we have some activations, which is going to be just a sigmoid function for us. And we, for the entire computation of these things, we only do a forward pass, as we have already seen in a previous slide. From the loss and the cost function, we can then get some gradients via, by simply forming the derivative. And then via backpropagation, we get gradients for each of the weights and biases of our activated layers. These gradients we then and outputs we can then pass to our optimizer, which again gives us some output for our linear layer. And now this optimizer can be something as simple as the backpropagation. So this simple backpropagation algorithm, basically, where we only give it some fixed step length or learning rate and feed back those gradients, basically. All right. Do you have any questions so far? Maybe post them in the chat while I set up a quick demo. So for this, we have a Jupyter notebook. And you can find this Jupyter notebook at the following link. Let me open this up real quick. Here we go. You can find this at this GitHub page. So if you want to follow along, the requirements for this are really minimal. So we have NumPy and Matplotlib. So there's not really any framework like PyTorch or TensorFlow used here right now. This is something I would like to do in the future, but it's not yet done. So let's first look at those imports we have right here. So we have some linear model, L2 loss, some optimizers, and the rest is just utilities. So let's maybe look at the linear model first. Don't worry, I'm not going to go too much in depth into the code, only the bare minimum. So for our linear model, we have linear layers, which are comprised of some weights and some biases. And so we can call this linear layer, and it simply does a forward pass. And this forward pass, I can zoom in on the text. Yes, just give me a second. All right, is this okay? Maybe a bit smaller. Yeah, that should be okay. Right. Okay, perfect. So for our forward pass, we only have here what I might have to say, this is already a slightly different forward pass than you might be used to. Namely with this sigma, WD, and BD. These are going to be used for our optimizers later on. because we need not only our model evaluated at the current weights and biases, but also at some disturbed weights and biases. So this is going to be basically our step length. And if the step length is given, we want to modify our current weights and biases for the network and compute our output with this. And then what we do is just multiply the current, so the new weights with our input, add our biases, which we repeat for in case we have several samples. So in case our batch size is greater than 1. And that's basically what our linear layer does. And then we also have a backpropagation, of course, which is the standard backpropagation you know. And we have some apply update, which simply applies an update to our current linear layer. And then we have an activated layer, which now includes some nonlinear activation function. And this is used for keeping track of derivatives which do not actually require any parameters to be updated. But this is nothing you need to concern yourself too much about. What's now important is the linear model. So as I said in the beginning, this is simply a dense neural network. So we have a certain amount of layers. This is going to be input layer, hidden layer 1, hidden layer 2, and output layer. Of course, these can be customized, as we will see later on in the working demo. And yeah, this model is simply an accumulation of linear layers, and we also assign this model a loss function, which in hindsight might not be the best idea. It would be better to do this outside of the model, but that's the way it is right now, and in a future iteration this will be done outside anyway. All right, and then we have some evaluation of our model. And again, we want to allow the evaluation of our model at some perturbed weights and biases. And since, if you remember, let me maybe go back for a second to the presentation. For the gradient descent method, we had that we assemble all of the weights and biases into one huge vector. We also do this for higher order methods. And this is why in the code we have here this section, which basically takes care of splitting up all of the weights and biases, or assembling it into one vector and splitting it all up again after doing an optimization step. All right, then we have some training and some training optimizer. I'm not going to go too much in depth for these because this is basically just calling optimizer step. So we have to look into optimizers anyway. And that's basically it for the linear layer. Let's maybe have a look at our optimizers, which we have. So a basic optimizer is going to have a step and a get search direction function. So for example, we have a classical descent method. So for a descent method, we have an optional line search, or for regular gradient descent method, we would just have a fixed learning rate here. And then we have some get direction function, which only yields the negative gradient of our current model, weights and biases. And in our step, we compute this gradient. So we get our direction via this get direction function. We get our step length, and we return our step length or learning rate times the search direction. So this is a standard descent method, nothing higher order so far, just classical first order. Then we have a Newton type method. So this is already the first higher order type method. This is still somehow an abstract method, so we still have to specify how to get directions, how to update matrices, and so on. But we already set some initial matrix, as I've mentioned earlier during while talking about the slides. So we have some M0. Before it was H0. Here I chose M for matrix. And we have now this different method of computing a step, because we now perform once a matrix update, which still has to be okay, something just happened here. Okay. So okay. Thanks for faving my channel. All right, so here we got some update function for the matrix and some line search, but maybe let's go straight into some quasi-Newton method, namely the the BFGS method. So this is one fully implemented quasi-Newton method here. And here I guess you could see most of what's going to happen. So for the BFGS update, we do the following. We first check if we have already computed a previous gradient. If not, we just compute it down here and return. So do nothing basically. This is for the first step where we do not have any information yet about any previous iterations. And then once we have already done our step, we update our current matrix by doing this update down here. So we take our current matrix and we perform a rank 2 update. So this is basically just some vectors multiplied together. As I said, the theory behind how these updates work is really complex, so I'm not going to go too much in depth here. Just take away, this is the original matrix plus some new, you could say, step matrix. And then we have some line search, and for the BFGS method, the line search Powell-Wolf. So the Powell-Wolf method has been proven to be an effective line search method. All right, so this is all I want to talk about, basically the back end of the code. Let's now go to the actual Jupyter notebook where you can see what's going on. Okay. So first of all, we start with some arguments. So in the first step, I just want to show you the linear model in action for the simple backpropagation algorithm. We define some maximum steps. So in case our method does not converge, we have some break-off criterion. You will see later on some of these methods will not converge because not all of them have been globalized, not all of them use the appropriate line search methods, but that's okay. This is, as I said, still a work in progress, and I'm just here to give you some idea of what might be possible. So we also have some target loss. So in case we reach this loss, we also want to break. We have some random seed. We have some amount of input samples, which is rather small. This is because also our model is really small. And this is the case because higher order methods, as I have implemented them so far, are really memory intensive. So in this case, we have 12 plus 60 times 2. So we have 72 parameters, which already, 72 times 2. So we have 144 parameters, which already yields a matrix of 144 times 144. Still rather small, but depending on the layer sizes, this matrix will grow really, really fast. And for this demo, I chose a rather small model just because I wanted to show you how the iteration count looks like. And we will also have a look at a slightly bigger model afterwards as well. We just consider classical tool loss because that's all we need right now, all I have implemented right now. But as I said, I want to do this in the framework of PyTorch, so all of the loss functions will be available then. So first we generate some training data, and let's first have a look at what this training data is going to look like. So I have this here on my slides for our numerics. So we have some only two-dimensional input, x and y, and we have some classification output, either 1, 0 or 0, 1. So basically we have some xy scatter plot, and we want to do some clustering of these inputs, or basically some categorization. So this is the setup, and we want to now have the, I'll get maybe to this a bit later on. Okay, so this is the setup. We have some XY data, and we have some classes 0, 1, and 1, 0. And then we can choose from a lot of, so first we have our linear model, which we just set up with a fixed learning rate. And then we have a choice of all of those optimizers. Note that only the first two and the last one are actually higher order. The rest are first order optimizers with certain line search strategies, which I implemented just to get a comparison basically on how well these higher order methods actually work. Right, maybe let's execute all of these cells so we don't have to do this afterwards. And then we have our training loop. So in our training loop, we basically do the following. We do the worst possible batch selection. So in each training loop, we choose some batch, and we do not even do anything such as epochs because our model is too small anyway, so that selecting small batches will even have a small speed up effect. Then we get our input, which is this random sample. If our optimizer is not set, then we just do, now if it is set, sorry, we do an optimizer step. Otherwise, we do just a regular stochastic gradient step. Then we compute the total loss. And we write this to our keeping track array, and we visualize what our model is doing at the current iteration. All right, so let's run this. I'm going to turn off visualization, so we have some pretty pictures afterwards anyway. So if you let this run, you can already see this. So for now, we only have a simple backpropagation, and it does not need the full 10,000 iteration. It only needs 4,400 iterations, and this is the result. So our model classifies all of the blue areas as crosses and all of the yellow areas as circles. So this is actually correct. And we can have a look at the training progress as well. But this is the way the code works right now. For having a look at the convergence properties, I'm not going to run all of these things here. Maybe let's have a look at the inverse BFGS just because it's interesting. We can let this run again. Okay, progress bar is doing weird stuff, but it doesn't matter because this should be done after a rather small amount of iterations. So you can see here, this method already terminates after only 141 iterations, as opposed to 4,400 iterations as the stochastic gradient descent took. Of course, I have to say I only used the bare minimum of stochastic gradient descent, so there is no optimization going on here at all. So no learning rate scheduling, no momentum at all. So take these results, please, with a grain of salt. But again, we see that the model actually produces the correct output afterwards, even though we have a really, really small margin down here. All right, so that's the code for now. Now let's look at the actual numerical results. So how well all of these methods perform. So I let one example run here for some time. So this is the initial output of our model. It was always the same, just this none-saying gradient. Sorry for the small numbers, but I think the images are rather self-descriptive here. So the initial output of all the models was the same. And then we let the training run. And this is here in percent of training, not in iterations. For iterations, you can look down here. So the backpropagation after 750 iterations already took some form, but the quasi-Newton methods, which are the last ones, down here you can see they already after 50 iterations only have a huge progress on classification. So the blue ones are already mostly classified correctly, or also the orange ones. Note the iteration numbers are slightly different than in the example I showed you earlier. That's just because the random seed was a different one. All right, let's go further. So 20%, 30% of iteration, and you can see the quasi-Newton methods already converge really fast to some very strongly defined solution, whereas all of the other methods take rather long. And what's also interesting, for this simple model, you can see that there is not only one solution, but this method down here, which is simple gradient descent with Bacilli-Borwein line search method, converges to a completely different result. So there was a question, does higher order mean also higher computational effort? Is it slower? Yes, it is slower, and I'm going to talk about this in a few slides also. So it is computationally slower, but it still yields a lot of benefits, especially if combined with line search methods. But more on that later. So this is basically just nice graphics, and this is the final output we get. So for all of the methods, we get correct results. And this is now the numerical behavior of our error. Again, sorry for the small numbers, but we can see classical backpropagation and a simple line search method, which is the Armio rule, they behave rather similarly. Sorry for not explaining what these methods do exactly. This would go rather deep into the mathematics of it all. But maybe just on a very low level, this is the classical stochastic gradient descent. This is a deterministic line search method. And this BBV2 and BBV3 are, as the graphics might already tell you, experimental or non-deterministic line search methods. So this BBV3, the Bacilli-Borwein variant 3, you can see it converges really nicely up to some point and then does strange stuff. So then it just completely breaks down. This is what you can also see in the images here, or cannot see. The image I extracted here was actually at this lowest point. So you would really have to take care to stop the training process at some point where you know it has already converged, which in practice is, of course, not really feasible. It is rather bad. But all of the other methods, they converge deterministically. All right. Let's have a look at some more real-world example. Sorry for the bad pun here. So we want to do, again, classification, but now we want to have more than just 10 inputs. We want to classify on this pixel map English-speaking and non-English-speaking countries. Very vaguely speaking, of course, there's more English-speaking countries, but that's just the ones I selected here. And so for our classification, we have basically this map of English-speaking countries here. And our input is the following. So we have these blue crosses for English-speaking countries and orange circles for non-English-speaking countries. And in this case, we do not even differentiate between oceans and non-English speaking countries. So this is really a really basic example. You could theoretically add a third category for oceans, but I'm not going to do this here. It's just for numerical investigation here, so for convergence speeds. And this is the initial output of our model. So any Anything above 1 would be an English-speaking country. Everything above 0.5 would be an English-speaking country. So in this case, nothing would be categorized as an English-speaking country yet. And then we'll let our different methods loose on this example. So we see here our backpropagation algorithm classifies most of the pixels correctly. Maybe I should say that the size of the network is still relatively small. So the layers, I'm going to put them in the chat. The layer sizes are 2, 12, 32, 12, and 2 again, which is already significantly larger. Which is already significantly larger than our 2, what was it, 2, 6, 10, 6, 2 model earlier. But this model already comes at the limit of the current implementation. So this is one drawback I will talk about later. Anyway, for the results, so you can see that most of those methods already classify it relatively well. The quasi-Newton methods struggle a bit with those small areas, but that's something which can be optimized away. In general, they do converge. Now for some convergence speeds. This is probably what you were waiting for the whole time. How long does the computation actually take? So actually, the next slide here might be even more interesting for you. So here I set some threshold. I wanted my loss to be less than 20. And then I let my algorithms run to completion. All right, maybe let's go. Yeah, this is the most interesting one. So the loss threshold of 30. Here all of the methods except for the Basel-Bourvin 3, which you could already see earlier, does really strange stuff at some point. So all the methods actually converged for this threshold, and the backpropagation took 7,400 iterations, which seems large, but it is rather fast when you look at the time. It only took 21 seconds to train the network. This is because each iteration is really fast. In comparison, the quasi-Newton method, in the sense of iterations, it converged really fast. So it only took about a sixth of the number of iterations as for the backpropagation algorithm. However, the timing is really bad in this case. That's because in each step we have to solve a linear system, but this is actually not what takes most of the time. It's the line search algorithm that consumes most of the time, which also leads to the fact that we take more than 5 minutes computing those. But there is a, let's say, light at the end of the tunnel somewhere, because we can combine different line search methods. So we can use different line search methods here. For example, as you can see here, the Basel-Bourvin method version 2 is super fast. But this is only a first order method here. However, there is so the results I got during experimentation with these quasi-Newton methods and line search methods, these results suggest that if we combine this super fast Basel-Borwein method with quasi-Newton methods, we might actually get a super robust and relatively fast method for training neural networks. So, as you might remember from earlier, or maybe not, this Basel-Borwein method, this line search method, is only a heuristic model or a heuristic method. So we do not have any guarantee that it will converge. On the contrary, for this quasi-Newton methods, we actually have a guarantee that they will converge to a minimum. And this is also one of the main advantages of these quasi-Newton methods. All right, with this, my talk comes to a conclusion and an outlook. So the conclusion we have drawn here is higher order optimization methods look promising, especially when we look at iteration count. But the line search method can be extremely slow, as you have seen in the example, and solving the linear systems involved can also be slow. Whereas the solving of the linear system is not as much of a problem. And the memory usage can be extremely high because having, let's say, a parameter count in the millions will lead to a matrix in the million squared. So this is really not feasible, especially if we want to store the entire matrix. But there are some, oh, sorry, the slides have already skipped again. So let me say the outlook again. Okay, no, it's correct. So for the outlook, what is on my to-do? I want to test different combinations of line search and update methods, as I've already said. So for example, the Basel-Borwein in combination with BFGS updates. Also, you can check if inverse methods are available for some of these update methods. I haven't talked about this at all during this talk, but you can think of inverse methods as quasi-Newton methods which do not require the solving of a linear system. So this will also take away a lot of the computational stress. Then we want to use memory-efficient variants. So there are already some variants available, such as the limited memory BFGS, but I have so far not implemented it yet. This is still on my to-do. And one other thing that might be done is to apply higher order methods only to part of the parameters. So not do higher order methods for the entire parameter set, but for example, stochastic gradient descent for most of them and higher order methods for a small part. And one huge part on my outlook is also integrate this whole thing into PyTorch, which would allow the use of different optimizers, different loss functions, different models to be tested with higher order optimization schemes. And with this, I want to say thank you for your attention. And yeah, thank you, Herbert, for the Discord link. There is going to be a Q&A. I would be happy to see some of you there. And for now, thank you all, and I hope you learned something new today. Right, and as Herbert just posted in the comments, the next meetup is going to be on the 9th of June. Apparently about path planning for autonomous cars. So see you then, hopefully.